Okay, so this is lecture 8 of basic calculus 1. We just recall what we did in the last lecture. We introduced the limits when it is of one side, that is limit x goes to some a plus or limit x goes to a minus. So, that means instead of a neighborhood of the point a where we are concerned about the limit, we are taking only left neighborhood or a right neighborhood. So, there only our x will be varying, then that is one sided limit. Today we will be talking about limits at infinity. So, that means we will be taking limit when x goes to plus infinity or x goes to minus infinity. However, there is a problem because infinity and minus infinity are not real numbers. So, when you say limit x goes to infinity, we would be thinking that x should lie near infinity, but as infinity is not a real number, what is the meaning of near infinity? So, intuitively what it would mean that when whenever x increases without bound, that is what we mean when x approaches infinity. So, that means it takes positive values and it goes on increasing, that is the intuitive idea. In fact, what happens, you just recall the one sided limits. When we say limit x goes to say c minus, then x lies in a neighborhood of c which is a left neighborhood like c minus delta to c. So, here infinity is thought of as if it is a very large one, not a number, but it is beyond all the large positive numbers. So, what do we mean by a neighborhood of infinity? So, it would mean that x increase without bound. So, that means we will be concerned about x or points which are to the right of any real number, so to say. So, any neighborhood of infinity will be a left neighborhood in the form a to infinity, where a is any real number and we take the open interval, that means greater than all numbers greater than a. So, that is how we will be thinking about a neighborhood of infinity. Then our earlier definitions of limit would go to this, exactly the one sided limit, specifically the left side one, because it is approaching infinity from the left. So, that is how you may think of a neighborhood of infinity and go for a formalization. So, for this what we need is, suppose S is a subset of R, it should contain an open interval of the form this. That means, in the domain of definition of our function, a left neighborhood of infinity should be there. Of course, there is only one neighborhood here of infinity, the left one, there is no right one, there is no real number greater than that. In fact, that itself is not a real number. So, we will be thinking of functions defined from a subset of R, S to R, where S contains a neighborhood of infinity, an interval of the form a to infinity. Then we will be thinking as if x is bigger than a, and for all those x, and that nearness we have to formalize, of course. So, as you recall in the definition of limit, we would be saying, suppose it is instead of infinity it is c and we want c minus, limit of f x equal to L when x goes to c minus, left sided limit. In that case, what you will do? You will say corresponding to each epsilon greater than 0, there exists a left neighborhood of c, c minus delta to c, such that when x lies in this c minus delta to c, f of x minus L mod should be less than epsilon. That would have been the definition when it is c minus. Now, when it is infinity, its neighborhood will be something of the form a to infinity, or let us say m greater than m. So, the definition would be for each epsilon greater than 0, corresponding to that, there should exist one m, a real number m. Usually we denote for natural numbers or integers, where here it is taken as a real number. There exists a real number m, obviously is greater than 0, we are concerned about a to infinity. So, we can still limit, say it is bigger than 0, even bigger than 100 you can take, it would be the same thing. There exists one m bigger than 0, such that for any x in S with x bigger than m, So, now since S contains a to infinity something, so this we may say x bigger than m. So, automatically it is in S. So, m should be large, so that this interval which is a to infinity should be contained in S. So, that means a to infinity will become a subset of m, that is you can choose one m which is bigger than a also. Okay. So, corresponding to each epsilon greater than 0, there should exist one m bigger than 0, such that for any x in S with x bigger than m, this condition of nearness of f x to L should be satisfied, that is f x minus L mod should be less than epsilon. This would be our formal definition of limit x goes to infinity equal to L. So, we repeat again, limit x goes to infinity f x equal to L, or we say limit f x is x approaches infinity is L, if corresponding to each epsilon greater than 0, there is one m greater than 0, such that whenever x is bigger than m, you will have f x minus L mod less than epsilon. This is how we will be defining the limit at infinity. So, let us say for example 1 by x, function is 1 by x. So, for any x bigger than 0, this is 1 by x is defined. So, the domain is 0 to infinity, 0 is excluded, your S is that. So, obviously that contains any a to infinity where a is bigger than 0. So, now to see this limit condition is satisfied, we guess that it should be 0, because once x becomes larger and larger, 1 by x becomes smaller and smaller. So, we say 1 by x becomes 0, that is our guesswork. So, now let us see how to justify. So, that means corresponding to each epsilon greater than 0, we should have one m such that whenever x is bigger than m, 1 by x mod 0 is L here should be less than epsilon. So, how do we find it? We choose your m, we have to find one m corresponding to epsilon. So, suppose epsilon greater than 0 is given, we choose m to be 1 by epsilon, that is what 1 by x says. So, now if x is bigger than m, then 1 by x will be smaller than 1 by m, and 1 by m is smaller than epsilon, that is what it says, or even you take m equal to. So, it is really equal to epsilon. So, now let us verify, choose m equal to 1 by epsilon. If x is bigger than m, then x is bigger than 0, and 1 by x minus 0 mod equal to 1 by x, which is smaller than 1 by m equal to epsilon. So, 1 by x is smaller than epsilon, therefore, limit 1 by x equal to 0. So, we are just checking whether our notion of nearness, as x becomes very large, nearness of 1 by x to 0 is justified by our formal definition. That is what it says, yes, it is justified. All that you have to do is choose m appropriately. So, you choose m equal to 1 by epsilon. Even if you choose m is smaller than some m which is smaller than 1 by epsilon, that will also work. Okay, so, this is limit x goes to infinity, that is when x becomes larger and larger. We will be concerned about the other infinity, that is limit x goes to minus infinity. Okay. So, again the intuitive idea is that x approaches minus infinity, which means without any bound x becomes smaller and smaller in the negative one. So, x goes to minus infinity. Again, to formalize, we would think a neighborhood of minus infinity. So, our notion is that infinity is to the right of every real number, minus infinity is to the left of every real number. So, it will be negative, that is why it is minus infinity. But then infinity and minus infinity are not real numbers. So, what is the notion of a neighborhood of minus infinity? Again, just like for infinity we take a to infinity, here we will choose a neighborhood, we will be defining something like minus infinity to some real number b. You can take b to be negative here also, that is okay. Any real number b also you can take. So, such a thing we may be thinking of as if it is a neighborhood of infinity. So, here limit x goes to minus infinity will be really something like x goes to c plus. From the right side we are approaching minus infinity, that is the intuitive notion. So, when x becomes near minus infinity, we would see that f x remains near L. So, just as earlier, when we say limit x goes to minus c plus, we would consider for every epsilon greater than 0, there is the delta, such that if x belongs to c plus delta. So, here it is neighborhood of c, and that is suitably translated to x belongs to minus infinity to b. For x belongs to this minus infinity to b, we should have f x minus L mod less than epsilon. That is exactly the definition of limit. We would start with any subset S, a subset of R, which should contain some interval of this form. So, once it contains an interval of this form minus infinity b, if you take anything smaller than b, say minus infinity to d, where d is smaller than b, then that minus infinity to d is also contained in S. So, that is neighborhoods of infinity should be contained in S. That is our precondition for defining this limit. Then S is the domain of a function and L is any real number. In such a case, we will define limit of f x equal to L as x goes to minus infinity, and that will hold if and only if what happens, corresponding to each epsilon greater than 0, there should exist one number, instead of b we are writing m, greater than 0, such that whenever x is smaller than minus m, we are taking negatives always now, because anyway we are concerned with the neighborhood of minus infinity. So, x should be less than minus m. For all such x, we have f x minus L mod less than minus epsilon. So, that means corresponding to each epsilon greater than 0, you should get some m, such that whenever x lies here, m is smaller than minus m, m will be some bigger, minus m will be smaller. So, this is 0. Then for all such x, f x is lying epsilon close to L in that neighborhood, that is f of x should lie between L minus epsilon to L plus epsilon. So, we say that f of x remaining near L when x lies near minus infinity. That is the notion which is formalized here. Let us see for our earlier function 1 by x how it is giving. That intuitively it says that when x becomes smaller and smaller to minus side, then 1 by x becomes larger and larger. So, on the other hand, if you say x becomes bigger and bigger in absolute value, but remains negative, that is x is chosen this way, right. Then what happens to 1 by x? 1 by x should be coming back here and it should become closer to 0. That is what our intuitive notion says. So, we are going to check limit x goes to minus infinity, 1 by x should be equal to 0. So, how do we check from the formal definition? That means, given any epsilon greater than 0, we should be able to find one m bigger than 0, so that whenever x is less than minus m, 1 by x mod should be less than epsilon. So, as earlier we will be choosing our m. So, suppose epsilon is bigger than 0, again we choose m equal to 1 by epsilon. So, whenever x is less than minus m, then we would find that 1 by x will be bigger than minus 1 by m, right. So, that is the idea of choosing this m this way. Okay. So, let us choose this m which is 1 by epsilon. Now, suppose x is less than minus m, then we find that 1 by x is bigger than minus 1 by m, and 1 by x is also positive because x is negative. X is negative. So, 1 by x is also negative, but x is less than minus m. So, what happens for 1 by x? That is still negative, it is not. So, 1 by x is less than 0, that is what we write here. That 0 is greater than 1 by x, that is 1 by x is negative and it is bigger than minus 1 by m. But minus 1 by m is epsilon, minus epsilon. So, we get 1 by x is bigger than minus epsilon. So, 1 by x minus 0 mod, which is 1 by x mod. Now, since x is negative, it becomes minus 1 by x. since 1 by x is bigger than minus epsilon, you would say minus 1 by x is smaller than 1 by epsilon, and that is what we it is 1 by epsilon, that would give you only epsilon. So, minus 1 by x is bigger than minus epsilon. So, minus 1 by x should be smaller than epsilon, that is what it is, and that condition is satisfied. That is, for any epsilon greater than 0 given, we choose m equal to 1 by epsilon. We find that if x is less than minus m, then mod of 1 by x minus 0 is less than epsilon. Therefore, the limit condition is satisfied, and we claim, our claim is proved, that limit x goes to minus infinity 1 by x is also equal to 0, as limit x goes to infinity 1 by x. So, in both the cases it goes to 0, that is what we have seen, but it may not happen always, because this is looking very symmetric 1 by x for positive or negative, that is why it is happening. Okay. So, let us take some more examples and see what happens. So, suppose I have the function as 2 plus sin x by x, this is the function. We are required to find its limit as x goes to plus infinity or x goes to minus infinity. So, obviously, we will be concerned about finding the limit of sin x by x also. Okay. So, how does the function look like? If you, it is just shifted to 2 units shifted to the top, 2 plus sin x by x. This is curve really sin x by x when starting from 0. So, it is shifted 2 units and curve looks like this, the blue one. This is y equal to 2 plus sin x by x. As we see, when x goes to infinity, these oscillations become smaller and smaller, it becomes 0. Similarly, on the left side, and this 2 remains. So, the limit should be 2, that is our guess. Okay, let us find out how it happens. So, suppose x is bigger than 0, we are trying to find out limit x goes to infinity now. Minus infinity we will tackle separately. So, for that we can assume x is bigger than 0, even x is bigger than 100 we can tell, because x should be lying closer to infinity. So, suppose x is bigger than 0, for this x, these types of x, we have this inequality satisfied, right, because sin x lies between minus 1 to 1. So, x is positive, divide by x. So, minus 1 by x is less than or equal to sin x by x, less than or equal to 1 by x. Why are you doing it? Obviously, we will be using sandwich theorem, because we already know the limit of minus 1 by x and 1 by x as x goes to infinity. We know that limit of 1 by x as x goes to infinity is 0. What about minus 1 by x? Well, it is just minus sign. So, that is also going to 0. So, by sandwich theorem we say that limit of sin x by x also goes to 0, because this goes to 0 as x goes to infinity, this goes to 0 as x goes to infinity. So, remember that sandwich theorem we have proved or we have mentioned only for limit x goes to c, but that also holds for x goes to infinity, because same neighborhood idea. So, by using the neighborhood idea again here, sandwich theorem also holds for when x goes to infinity, limits at infinity. So, with that in mind, we have done this minus 1 by x to 1 by x estimate, and that shows limit x goes to infinity, sin x by x goes to 0. Now, what about limit x goes to minus infinity? Well, for that we may assume x is less than 0. Then instead of doing it fresh again, because we have done already sin x by x, we will substitute x equal to minus t, right. So, now we are going to do some limit calculation here. Limit x goes to minus infinity is same thing as limit t goes to infinity, because t equal to minus x or x equal to minus t. And what happens to sin x in terms of t now? It is sin of minus t by minus t, but sin of minus t is equal to minus of sin t. So, these two minus cancels and you get limit t goes to infinity as it is, the ratio becomes sin t by t, and that is same thing as sin x by x, x goes to infinity. The variable is does not matter, because the same neighborhood idea. So, this equal to 0. That means, limit of sin x by x, whether x goes to infinity or whether x goes to minus infinity, equal to 0. that conforms to our intuitive idea we explained here earlier. So, once this limit equal to 0, you can go to 2 plus sin x by x, then that should be equal to 2 plus 0, right, that is 2. That is what we say. Hence, limit x goes to plus infinity or x goes to minus infinity, both the things we wrote here, of the function 2 plus sin x by x should be equal to 2. So, see how the estimates are helpful. We will take one more example. Let us say we are having two functions here, we have to find the limits at infinity, that is limit x goes to infinity of f x, limit goes to x goes to infinity of g x, where f x is given as square root of x and g x is defined conditionally this way. It is 1 when x is a rational number and it is 0 if x is irrational. Of course, its domain is 0 to infinity. So, when you say x belongs to q, it means here x belongs to q and x remains positive, both the things. And the second one is x is irrational and also x is positive, it is a positive irrational. For those x, g x is defined this way, it is 1 for positive rationals and 0 for positive irrationals. Only for positives it is defined here. Okay. So, now intuitively what it says, if f x, we want to find out the limit of f x as x goes to infinity, then as x increases to infinity, f x also is root x, that also increases to infinity, right. So, that means it will not remain near any real number. Suppose I say 100, now will square root of x remain near 100 for every x? No, if I take x equal to say 1000 square, then its square root will become 1000. So, it does not remain near that. For every epsilon, I should get one delta. So, for every epsilon, I should have f x minus 100 mod less than epsilon. It is not so, because it is becoming 1000. So, if I choose epsilon equal to 1, it does not. So, that is the argument that root x does not remain near any real number, it becomes larger. So, that is our intuitive feeling, and that you can justify through the formal definition also. So, that means f x equal to root x will not have a limit as x goes to infinity. Okay, what about g x? As x increases to infinity, so it increases. So, that means it will take rational values, it will take irrational values and so on. And we have the denseness of rationals, that between any two real numbers there is also a rational number, there is also an irrational number. So, that means as x becoming larger and larger, x goes through real numbers. Whenever it is rational, it becomes 1, whenever it is irrational, it becomes 0. So, it does not remain near either of them, it becomes 1, sometimes 0 and 1 and 0. So, it oscillates between 0 and 1, between these two values really, becomes 1 or 0, 1 or 0 at almost every point. So, that means when it remains in a neighborhood of infinity, it assumes both the values, so to say, right. So, it does not remain near any one of them, therefore, that limit also should not exist. That is what we say, limit f x does not exist, limit g x s goes to infinity also does not exist. Okay. So, let us do some more problems basing on this notion. Yeah, there is a note here which says that you can convert x goes to infinity to x goes to 0 plus by substituting x with 1 by x. So, here it is t equal to 1 by x and t goes to 1 by t goes to infinity. So, t goes to 0 plus. So, you would say that limit of f x goes to infinity is same thing as limit f of 1 by x goes to 0 plus, right. Similarly, when you say f of 1 by x, then x goes to minus infinity, would say that x goes to 0 minus. That means, from the negative side of 0, you will be taking this way and it is a new function f of 1 by x, there x goes. And on the other hand, if x goes to infinity, you will say f of 1 by x, where x goes to 0 plus, it is in the neighborhood of 0, but remaining positive. Sometimes this substitution is also helpful, because it can simplify some notation and some expressions. Okay, you may not have occasion immediately, we will see later.